My name is Manish Gupta, and in this video, I'm going to talk about OpenAI Clip, which is a model that connects text and images. So let's get started. What is OpenAI Clip? Clip actually stands for Contrastive Language Image Pre-training. So the name tells it all in some senses. It uses contrastive loss. It does a multimodal language image pre-training. Therefore, it's a multimodal model and it has been pre-trained on a special data set that these guys create using 400 million image comma text pairs. Specifically, the task that is used for pre-training is to predict which caption goes with which image, as simple as that. After the pre-training is done, they actually leverage the clip model in a zero-shot setting by using natural language to reference learned visual concepts or also to describe new ones. So essentially, if you have a new task, new classification task, you could still do that in a zero-shot setting by considering the class names as labels as captions for the task. Okay. It has been tested on 30 plus computer vision tasks, including optical character recognition, action recognition on videos, geo-localization, and several other complex vision tasks. What is interestingly observed is that a zero-shot clip model is often equivalent to a fully supervised baseline, and that to very strong fully supervised baselines. For example, on the ImageNet data, zero-shot clip is approximately equivalent to ResNet 50 model, which has been actually supervisedly trained using 1.28 million training examples, right? Clip, there are eight different clip models, and scalability basically shows that transfer performance is a smooth, predictable function of compute. So the performance just keeps improving as you increase the compute and train the larger of the eight uh, trained clip models. Okay. The clip models are actually available here, so you can read more about the clip models on OpenAI on github.com/OpenAI/clip. So clipping involves contrastive pre-training. What is contrastive pre-training, and why would one want to do contrastive pre-training? So contrastive pre-training is based on contrastive loss, which is which has become very popular. Let's say if you have a batch of n image text pairs, you know that for this particular image, this text goes with it. However, you try to explore all n cross n combinations of image and text, and then exactly try to predict which particular image and which particular text go with each other. Okay. More specifically, you train an image encoder and a text encoder together. So there is a caption, you train a text encoder to come up with an embedding for the caption and an image encoder to come up with an embedding for the image. In a multimodal embedding space, you essentially try to jointly train this image encoder and the text encoder so as to maximize the cosine similarity of the image and the text embeddings of the n real pairs in the batch while minimizing the cosine similarity of the embeddings of the remaining n square minus n incorrect pairings. Okay, so given this image embedding for the n images in the batch and the text embeddings for the n captions in the batch, you want to, of course, maximize the diagonal while minimizing the non-diagonal elements. So this is a very, very simple code that Clip folks have proposed so as to code up the contrastive loss. First, you essentially get the image encoding, text encoding, and then essentially use these WI weight matrices so as to learn projections of the image to a multimodal space as well as projection of the text to a multimodal space. And then you essentially compute the cosine similarity while also caring for temperature. So typically people try to consider temperature as the hyperparameter, the softmax temperature, but here they in fact treat it as a parameter and try to sort of learn it while doing backpropagation. Right? So the loss function that is used is a symmetric loss function, symmetric cross entropy loss. So where you compute cross entropy loss um, between logits and labels in the x and the y direction on in both the directions, and then take the average of that. Okay. So why do contrastive pre-training? Well, what else can you do, right? So you could basically train a transform-based language model where you could actually supply some sort of image embeddings and then ask it to generate text, right? So this blue curve is exactly that here, right? Or what you could do is to basically have some sort of a encoder and try to guess try to guess the captions as back of words, right? So this is the orange line, and then here is the clip line, basically the one that uses contrastive loss. So it's more or less similar to the orange line, except that the predictive loss is replaced by a contrastive loss. And well, as you observe, this is the accuracy. This is basically the number of images processed for pre-training. And as you observe, the green line is 12 times more efficient compared to a standard transformer language model and 4 times more efficient compared to a predictive equivalent. And that is why you would want to actually go ahead and use contrastive pre-training rather than the typical predictive pre-training. Now, while all this is good, where is the data set to pre-train this kind of a model, right? Popularly, several data sets have been used, like MS COCO, Visual Genome, YFCC 100 million, by several other people. But these data sets essentially do not have a very rich image text pairs at large scale. Right? Therefore, these authors essentially gathered their own data set called the web image text data set, which consists of 400 million image text pairs, where the text includes one of a set of 5 lakh popular queries. These queries contain words occurring at least 100 times in English Wikipedia, right? Or they are basically high, bigrams with high pointwise mutual information, or they are Wikipedia article names above a certain search volume threshold, right? If WordNet synsets don't occur in this set already, then these are also included, right? So as to make sure that the data is pretty balanced in that sense across all queries, they have limited the maximum number of image text pairs per query to 20,000. Okay. What is the architecture of the CLIP model? So they follow two popular architectures: ResNets and Vision Transformers. Okay. So in fact, they train 5 different ResNet models: ResNet 50, ResNet 101, and then models which are 4 times, 16 times, 64 times larger compared to the one of the awesome models on ImageNet called as EfficientNet. Okay. So the idea is that they have 5 ResNet models, one ResNet 50, another ResNet 101, and then 3 other efficient net style models, which are 4x, 16x, or 64x more compute intensive compared to ResNet 50. They also train 3 vision transformer models with different parameters, base, large, and so on, right? So overall, they train 8 different CLIP models, 5 dependent on ResNet architecture, 3 depend on the VIT architecture, vision transformer architecture. The text encoder, so there is an image encoder, there's a text encoder as well. So for the text encoder, essentially they always use a typical transformer with 63 million parameters, 12-layer transformer, 512 hidden layer size, and 8 attention heads with masked self-attention. They train for 32 epochs. This training is not simple. This pre-training involves the largest ResNet style model involves 18 days on 592 V100s. That's crazy amount of compute power. The largest vision transformer took actually 12 days on 256 V100s. So in fact, that takes slightly lesser, right? So these models have been trained from scratch. They did not use any pre-training. So rather than pre-training from ImageNet weights, and we'll see how that actually matters, right? So especially when you are training on such a large compute power and such a large data set, 400 million things, then probably you can ignore the pre-training bias that was already there in these image encoders, right? And as we discussed in the previous slide, the softmax temperature tau is actually directly optimized during training rather than being treated as a hyperparameter. So how is CLIP used for zero-shot classification? You have pre-trained, CLIP. So there is an image encoder, there's a text encoder, and of course you pre-trained it under the symmetric cross entropy laws, so as to minimize the cosine similarity for non-diagonal elements and maximize cosine similarity for the diagonal elements, right? So you have the image and the text encoder, which is nicely pre-trained. Now, how do you use it for classification tasks? So CLIP is actually promoted to be used as a zero-shot classification model, where the class names in those data sets are used as captions. So let's say if you are trying to do classification on a data set with like 100 dog breeds, you would use the names of each of those dog breeds as the text caption, and then try to sort of ensure that given an image, you can actually predict one of those text captions. So here is an example. You take the class names, and essentially you actually enlarge them a little by adding a few words here and there, like a photo of a plane, a photo of a car, a photo of a dog, and so on, and feed it to the text encoder. Whatever representations you get from the text encoder, let's say there are n different classes, so you get n different representations. You also use the image encoder to feed in the image, and then you compute the cosine similarity. Whichever has a high cosine similarity is a thing that you predict. So a photo of a dog is actually predicted with the highest cosine similarity in this case. Okay. Um, you could use directly class names as the text which should be encoded by text encoder, but that has three problems. One, in many data sets, class names are just IDs. There are no class names really. I mean, it's just like class 0, class 5, and so on. What do you do in that case, right? So that's a problem. The second problem could be polysemy. So two different kinds of things could have the same class name. For example, in ImageNet, there are construction cranes as well as the birds called cranes, right? So how do you then differentiate between them? Right? Similarly, in Oxford IIIT pet data set, there is a dog breed called as boxer as well as athlete could also be called as boxer, right? So therefore, you have to distinguish between those classes somehow. Right? Lastly, while pre-training, you have long text as part of the text encoding, right? While here, when you're doing zero-shot classification, you basically have just one word. Now, how is that justified, right? And therefore, what these guys did was to actually take the class name and add a prompt to it. So the prompts could look like that: a photo of a class label, a photo of a class label, a type of pet, satellite photo of a class label, and so on. Okay. In fact, another way of doing it is to do ensembles. You can actually use multiple um, zero-shot clip models by using different context prompts, such as a photo of a big class label or a photo of a small class label, right? And then you can actually try to come up with predictions and do majority voting. Now, this majority voting can be either done at the probability side or at the embedding side itself. So as to make it more efficient, it's better to actually do this ensembling at the in the embedding space rather than in the probability space on the logits, right? In fact, this kind of ensembling is also a very nice idea if you want to basically make use of GPT-3 kind of model so as to do labeling rather than depending on crowdsourcing for doing labeling. In some ways, it's sort of like doing crowdsourcing with multiple labelers. Yeah. So how does this zero-shot clip perform compared to equivalent supervised classifier? Hey, you may think that the game is not fair. We're comparing zero-shot model with a highly supervised trained model, right? But it turns out that the zero-shot clip actually performs really well compared to an equivalent trained supervised trained classifier. The best clip model actually has 76.2% top one accuracy on ImageNet, and this matches ResNet 50's accuracy where ResNet 50 actually has been trained on 1.28 million training images, right? So a zero-shot clip is really, really powerful, right? The prompt actually improves the accuracy by 1.3%, and ensembling actually improves it further by 3.5%, which is so awesome. Top 5 accuracy on ImageNet is 95%, which is way better than ResNet 50's accuracy, a trained ResNet 50's accuracy. In fact, it matches supervised Inception V4's accuracy, although the backbone is just ResNet 50, okay, for the clip model. In fact, as you see here, across 27 different data sets, we observe that if you take zero-shot clip versus you just take the ResNet 50 model and do a logistic regression classifier on top of it, you observe that out of 27 data sets, on 16 of them, zero-shot clip wins. Yes, zero-shot clip has its own problems. So it is weak on these data sets, which are more complex or more niche kind of tasks like satellite image classification, lymph node, tumor detection, counting objects in synthetic scenes, or self-driving related tasks like German traffic sign recognition and so on. Okay. So an immediate question is that, hey, how does zero-shot perform compared to supervised classifier, where you also allow your zero-shot clip to you also allow the clip model to use some of those labeled examples. So let's basically therefore call it few shot clip. Okay. So you have zero-shot clip and you have few shot clip, and then the idea is how does it perform? So what is a few shot clip? By the way, a few shot clip is a model which makes use of the same label space, same feature space, same feature space. Sorry. So you have an image encoder, you get the features out of the image encoder, and then you connect them to the output layer. If it's a 10 class classification problem, you connect it to a output layer of 10 classes, right? Of 10 different neurons, and then if you had 10 classes, then you will basically use, and let's say you were doing 4 short, then you would use 40 examples because you use 4 examples per class. That's the way few short clip can be arranged, right? Now, what is interesting to observe is the following. This chart basically shows number of label training examples per class and the accuracy score. Now, we show it across several tasks. So those gray lines show it across tasks, but the broad observations across different architectures are shown with colors. So ResNet 50 is there, SimCLR V2 is there, BitM, again, another awesome, powerful supervised learning model in ImageNet is there. And there is our linear probing clip, a few short clip in some ways, right? But then, you also see this horizontal line, that's zero shot clip. Of course, it doesn't use any labeled example, therefore it's a horizontal line. Okay. Now, what is interesting to observe is that zero shot clip is equivalent to a four-shot linear classifier, four-shot clip model. Now, how is that even possible? You might be asking, hey, I give like 4 examples per class, and then you're saying that it's the same as doing zero shot clip. Now, although that seems unintuitive, but it's very interesting to observe that when you are doing supervised classification, you're actually just giving the class labels ID. The classifier is not really learning about the text representation of that class. Okay, and it's missing on that very important piece of information. In fact, the few shot normal supervised learning must just infer the concept, the meaning of the concept indirectly from training examples. While Clip's zero shot classifier is beautiful because it actually makes use of the natural language representation of the class label so as to do this learning way more accurately and way more faster. Okay. So that's that. Um, Also, if you look at different sizes of the clip model, these are all different clip model sizes. Across 36 different data sets, people observed that as the size increases, as the size of these clip models increases, of course, the compute power required is larger, but then the error across these 36 data sets drops as well, which is so beautiful because, yes, if you scale the model larger, the power of zero shot performance actually is preserved. And in fact, it scales with the scale in the compute power. Right? This chart is very, very beautiful. So what does it say? It basically says that, hey, we have a zero shot clip model, right? And you have a few short clip model, right? So if you basically have like a CFAR 10 data set, right? It's a 10 class classification data set, as most of you know. So if you take 81 examples per class, or rather you take the image encoder of the clip and then you connect it to a 10 neuron output layer, and then you train it using 810 examples, 81 examples per class, 10 classes, right? Its performance is equivalent to a zero shot clip. Now that's so awesome, right? And if you take FER 2013 data set, 184 examples per class, then even then the performance is equivalent to a zero shot clip, which is great about the zero shot nature of the clip model. Now, how do clip representations actually perform compared to other ImageNet trained representations? Okay, so here what do we do? Here we basically take the clip model and use it in for linear probing. So essentially we take the clip representation, connect it to output layer, consider it like 1,000 class classification layer or whatever is the number of classes in the data set, right? And then these compare it with other models which have been trained on ImageNet. Okay. So there's this clip model, which is basically in a linear probe mode, you're using it. And then there are all these other models which have been trained on ImageNet. You compare it and you compare it across several computer vision tasks, 12 tasks here, 27 different set of tasks here. Right? The interesting part is that you see there are different models which are being shown here. And the ones which are, these kinds of stars right at the top are the clip models. They are all clip models, right? And they are vision transformer based clip models, right? While what you see here is ResNet style clip models. So what you observe is that the linear probe performance of clip models compared with state of the art models, it sort of shows that one, clip vision transformers are about 3x more compute efficient than clip ResNet models. So clip vision transformers are actually pretty efficient compared to ResNets. Okay. Interestingly, the best model is actually the VIT is one of those vision transformer clip models. One of those vision transformer clip models which has been fine-tuned at a high resolution of 336 pixels and then has been trained on one more epoch. Right? Clips features actually outperform the features of the best ImageNet models. As you see, the brown curve here with the stars is actually always the skylining curve. And it sort of outperforms the features of the best ImageNet model, which is basically the noisy student on 21 out of 27 data sets. So here 27 data sets average is shown. But then if you try to look at each of those data sets out of 27, 21 of them, basically Clip's features actually are better. These guys also tried to figure out the robustness of Clip to other data sets, to natural distribution shifts to other data sets which are similar to ImageNet, but somewhat different. So there are these data sets, ImageNet V2, ImageNet Sketch, YouTube BB, ImageNet Vid, ObjectNet, and so on. So as you observe, is a standard ImageNet with the typical objects and fruits and so on. ImageNet V2, then you have ImageNet R, and then ObjectNet, and so on. Several, and Object ImageNet Sketch, just sketch images, and so on, right? So what you observe is that on these kinds of data sets, a traditional ResNet 101 model trained on ImageNet data um, actually performs very poorly. On some of those data sets, it gives like 2.7% accuracy, pretty poor, pretty poor. While on ImageNet, it is really awesome, right? And of course, an awesome model. A zero-shot clip, on the other hand, performs equivalently well on ImageNet, but performs really well to these other ImageNet variants. Okay? In some ways saying that clip model is pretty robust compared to these other existing ImageNet, other existing models which have been pre-trained on the ImageNet dataset. In some ways, these models have been rather very fitted for ImageNet to a certain extent. A linear probe over the same benchmark of 12 and 26 datasets also shows that the clip models typically perform really nicely on average across these other datasets compared to all other models which perform really nicely on ImageNet but perform worse on these other datasets. Yeah. Now, people also try to compare it with human performance. So how does CLIP compare to human performance? They evaluate on Oxford IIT PET's data set, which basically contains, and the idea was that they asked humans to select which of the 37 cat or dog breeds best match the image. The human could also mention, I don't know, if they were completely uncertain, right? This was shown to 5 humans, so there is a 5-level parallelism with respect to humans, right? What you observe, here are the results, right? So there are 4 methods: zero-shot human, which basically means that people were just shown images and they were asked to guess, right? No training. Okay, and by the way, I'm very bad at figuring out dog breeds, honestly, right? Several people are. But these 5 humans, I don't know how good they were in terms of identifying dog breeds or cat breeds anyway. Yeah. Zero-shot clip model also, you have not told it the dog breed, so you've not trained it to identify dog breeds, but well, you have trained it on 400 million image text pairs, so it must have learned something about dog breeds and cat breeds anyway, right? One-shot human, you essentially show one image per dog or cat breed per class label, right, to humans and tell them, hey, this is what is there for your training, look at it and understand what it means. Two-shot human, you basically show 2 images per breed to humans so as to make them learn about the cat or dog breed, and then depend on their memory to remember things, right? That's that. So the accuracy overall, zero-shot clip has insanely better accuracy compared to human accuracy. Even if you do majority voting, you observe that the best human accuracy is 85, while zero-shot clip accuracy is still very high. Now humans do marks many times, I don't know. And if you basically ignore those cases, then the accuracy is somewhat better, 78, 79. And if you basically do majority voting on top of it, well, it's 86, but still is much lower compared to 93.5. Further, if you basically try to look at these different dog or cat breeds and try to see the accuracy, you observe that the blue curve is the zero-shot clip curve, and the orange and the green curves are zero-shot human and one-shot human and zero-shot human curves. So what you observed is that the categories which are harder for clip to predict accurately are also hard for humans in that sense. So it sort of shows a human-like nature, but still better in terms of overall performance. Lastly, what is important to sort of think through is this model biased? Is clip biased, right? Now, they do a very fancy evaluation. So what they do is the following. They use a data set called as fair face data set. So as it sort of says, it's a collection of several faces, right? And then they've been labeled for various kinds of things. One of the things that they've been labeled for is the race of the person. So black, white, Indian, Latino, Middle Eastern, Southeast Asian, East Asian. Okay. Now, to understand the bias in terms of classification across these categories, what these guys did was to add more categories. Yeah, of course, we are doing zero shot clip, so basically it doesn't matter. You can add as many categories as you like. So they added four categories called animal, gorilla, chimpanzee, orangutan, and three categories called as thief, criminal, suspicious person. Okay. Now, these categories were added to check if harms of denigration disproportionately impact certain demographic subgroups. Okay, so one important broad level understanding is that after adding these categories, when you ask zero shot clip, 4.9% images got misclassified into these four non-human classes. Okay, so 4.9%, about 5% images got misclassified here. Now, most importantly, out of those 5% which got misclassified into non-human categories, 14.4% were blacks. So there's a higher probability of labeling a black guy's face as these one of these non-human categories, right? So the model is somewhat biased. In fact, what I like about this evaluation is that they're pretty honest about the bias that the model shows, and clearly there is more work to do to avoid such bias. But at least it's important to identify, yes, that there is some sort of bias in here, right? Uh, so that's that. Also, what they observed is that there's an age-based bias. So people aged between 0 to 20 had the highest proportion being classified into this category at about 14%, right? Into the non-human class category. When you look at the crime-related categories, they observed that in fact, about 16.5% of the male images were classified into crime-related classes, while 10% images were female images were classified into this. So there's a gender bias there. So more of males were basically classified into crime-related categories. And as you observe, yes, there is interestingly a bias towards whites here, where a lot of whites are actually classified into crime-related category. Now, given that there is this, again, if you look at the age group, then 0 to 20 years old, in fact, a lot of them were actually put into the crime-related category, like 18%. Now, who knows why, right? So to handle this, what they did was to actually add yet another class called as child, right? So essentially not just your typical 7 classes, black, white, Indian, Latino, and so on, right? And not just these other 7 classes, animal, gorilla, chimpanzee, orangutan, thief, criminal, and suspicious person, but you also had another class called child, right? And what you observe is that adding this new class called child drastically reduced the number of images of people under 20 which were classified in either crime related category or non-human categories. Okay, so therefore some of this bias can be sort of reduced sometimes by actually just adding an extra class label, let's say called child, right? And then that reduces the overall bias that you observe for a particular zero shot task. That's about clip, and I'm just going to show you different variety of data sets where people have tried clip, and or these authors have tried clip, and they found it to work really well in most of these data sets. In some cases, yes, it screws up. For example, here is a data set with different types of food. Here's a data set with different types of indoor scenes, or there's a data set, YouTube BB data set. This is a satellite images data set where it went wrong. Rather than predicting annual cropland, it predicted permanent cropland, right? Uh, Lymph node tissue data set to binary classification, whether it is lymph node or not. There's the data set of CFAR10 data set, right? The popular CFAR10 data set. This is an adversarial data set which basically asks for presence or absence of a particular animal in a large setting. So you have to basically look at this animal and quickly predict which of them it is, right? Clever data set, which is about synthetic objects and so on. Facial emotion recognition data set, or Caltech data set about animals, sports related data set, ImageNet rendition data set. From the rendition, try to figure out which animal it is. Other data sets like Oxford Triple IT data set, um, which is about different breeds of cats and dogs. And then there's a matched frequency ImageNet V2 dataset, another example of a CFAR dataset, aircraft related dataset, figuring out which particular aircraft it is, Boeing 717 and so on, right? Uh, Dataset country 211, I mean, dataset about where you find these kinds of animals, which countries, or cars related dataset. indoor, outdoor, place-related data set, right? Type of place, right? Satellite image data set. So this is satellite image of what kind of thing? A church or a roundabout or an intersection and so on. Human activity kinetics data set, ImageNet, the traditional ImageNet, of course, flash data set, birds data set. So many data sets that people have tried these models on. And as you see, in most of these cases, the CLIP model gives you really good results. Right? I'll not go over everything, but as you see, there is a large variety where CLIP model has been shown to be promising. In fact, CLIP model was proposed in 2021, and in 2022, it remained as the most popular model for modeling text and images together. Uh, in summary, let me summarize this video. So CLIP is a model which connects text and images, right? It's a multimodal model which can be applied to any visual classification benchmark by simply providing the name of the visual category as the text label, right? It sort of performs in a zero-shot fashion, much similar to GPT-3. It has been pre-trained on 400 million image text pairs. It has been tested in the original paper on 30 plus some computer vision tasks involving optical character recognition, action recognition on videos, geo-localization, and so on. What has been observed is that the zero-shot clip is actually very, very powerful. It's often equivalent or better compared to a fully supervised baseline. For example, zero-shot clip on ImageNet actually performed better than an equivalent fully supervised testnet 50, supervised using 1.28 million training examples. CLIP has two different architectures, five models available, five checkpoints available for ResNet 50, and then other three for vision transformers. And interestingly, as you increase the scale, you observe that the zero-shot accuracy improves. Right? You can read more about CLIP models here. So that's it. Thank you for watching. Hope you liked the video. Connect with me on my LinkedIn there or visit my research on my homepage there. Thank you.